Hopefully we're live. I'm checking the live stream to see if we are live. Usually it takes a minute for me to see myself weirdly on the thing. So let's see. Because the last time we kept trying because it was our first time, and by not seeing anything, we had the impression that nothing was working, but it just takes a while. So here we are. We're live. We're live. Woo-hoo. So welcome, Thomas, again.
Yeah, hi, Luca. So this time of the week again.
Yes, yes,
Time
it's
is a
crazy, right?
tradition, right?
Absolutely, it's already a tradition. So Friday, 5 p.m. Europe time, whatever it is, in other parts of the world, we're meeting because we want to chat about compilers, deep learning compilers in general, and the session is called the Thunder session because we're developing a compiler called Thunder. But we are most interested right now is in understanding why compilers are even important right now and what they enable to do and how you can think about them and should care about them. And then we're taking it step by step. So we did an introductory thing. Today we'll have a bit more code, and then we'll go from there.
Yeah. So last time we talked about how GPUs as the compute device that everyone uses for the fast things work, and we had that the CPU essentially can queue kernels on the GPU, and then the GPU will asynchronously execute them. And so this already creates like a lot of things that we care about. So if we have, like last time, just a small MLP with a linear, a relo, and another linear, we have that like to the CPU, all these operations are just in queue a kernel. But to the GPU, of course, the linear with the matmul is much, much harder than the relo. And so one of the questions is, can the CPUs actually feed the GPUs fast enough? And so the answer is, well, not really, at least not anymore. When Luca and I started in this, that was still like reasonably well. But nowadays, you then have gaps. And obviously, if you have exciting GPUs, having them sit idle is like losing out on excitement.
Yeah.
Um, and so we want to find ways to close these gaps, essentially.
Yeah, and also there's one more thing, right? Because it's not only that the CPU doesn't enqueue fast enough necessarily, but it's also that each launch of these, like you have a kernel and then you have another one, another one, another one, and if you execute all the operations one after the other, there are a few things. Even if the CPU is not involved at all, even if the CPU is perfect as has enqueued everything it had to, there's still waste lying around, right? So there's some time here where that is spent doing things that are not computing.
Yeah, and so in particular, if you have like a string of kernels that all do small things, one of the bits is that, well, yeah, the kernel can like keep stuff in registers on the GPU, but between the kernels, we always write back to the global GPU memory. And while that is fast compared to other things, it certainly does take a while. And so the GPU basically, when you saturate it to 100%, it does, in a very Mickey Mousey way, of course, it does two things. It computes and it loads things from memory and stores them back. And so obviously, you want to get as much compute in if you can reduce the amount of memory transfer, and in particular, the time that the memory transfer takes while the GPU waits for the data to arrive or to be gone, that will be a good thing.
Yeah, and this, just to clarify, this is GPU, right? It's not, we're not talking about moving stuff from CPU memory, from main memory to the GPU memory. So unified memory, these things don't help in this case. It's more like you have memory on the device directly, and you need to take data back and forth to the tensor cores, and the tensor cores have gotten a lot faster than the memory transfer have gotten faster in the latest architecture. And this is why we need to make sure that we spend as much time as possible doing stuff here, right? As opposed to, oh, do one small thing here, great. Then, well, here, of course, not in just one, in many of them. And then place the numbers back, and then, oh, now we need to do this second thing. Okay, great. So we need to bring exactly the thing that was there a moment before, but bring it back.
I mean, just as in the olden days, you were always like lost. You had lost when the computer started swapping from main memory to disk. Now here, like the GPU RAM, the high bandwidth RAM is the thing that's slow, and we want to keep it in the shared memory, which is kind of a fast cache that's an order of magnitude faster, or in registers even to have things really fast. And so one of the obvious ways to do this is when you have like lots of little things, instead of like executing them one by one. And if you run a PyTorch program, for example, and last time we discussed how that is a good thing in terms of observability and debuggability, that it will just execute one thing after another as the code is executed. But from an optimization point of view, you're missing out there, because basically you have all these separate little instructions, and you could go a lot faster if you compile that to like one big thing.
Right. And when we talk about thing, we're talking about something called a kernel. So what is a kernel essentially? And we're talking about this thing here, right? Where that this is a kernel, this is not a kernel, this is another kernel. So what is a kernel fundamentally?
Yeah, so that is one function we execute on the GPU, and it has to be self-contained in the sense that everything that's coming into the kernel comes from memory in some form. And if it wants to return results, it has to return them through memory again. And so at the end of the kernel, all the results that have been computed need to be written to the memory. And
exactly.
So having fewer kernels means you have less points where you have to have everything written.
And also there's a time for kernel launch itself. So kernel launch time is a compound thing of multiple things, but it's pretty clear right now that on one side there is what we call PyTorch Eager, and all the benefits of Eager framework. Eager is just, a Python program is eager. When you write hello world, that is eager, because the effect will be every line will be executed after the other. This is what we mean by eager, which is great because you can step through your program. Your program crashes at some point, you can immediately inspect it. It will break there and not break somewhere else because you built a graph of some kind, and then later on it breaks and there's no relation or very weak relation between the two. And then it executes immediately. So you don't have to hit enter, wait for stuff to happen, and then later on, and then the iteration cycles are really low. Your own iteration cycles. Eager, just, it runs line by line. But now we're talking about putting things together. So do I have to write a bigger, instead of many of this kernels, one per, 1, 2, 3, 4, 5 that we wrote up here, from here, we want to get to something that is one bigger, let's say, CUDA file, even though maybe we don't materialize it as such, or maybe yes. And then with a bigger set of, and where 1, 2, 3, 4, 5 are basically sections of this program, right? So who does that?
I mean, you want one big function, right? And so one way of doing it, like, is go and write the .cu file yourself. And obviously, there's quite a few projects that do that and try to do like the best possible thing from scratch. And it is very instructive. So, for example, one of the maybe most popular projects of this from scratch nature is Andrei Karpathy's LLM.c, where he goes and and now that it's a lot of people really, because they open sourced it, and there's lots of contributors, and they write something like GPT in plain CUDA, and so this comes under the name of LLM.c, and is a really great project to see like what's going on, but I mean, we like PyTorch, and so writing all the CUDA code yourself, that is very much not like writing PyTorch. And so the idea is, well, can't we have something that takes my PyTorch code and translates it to something that's really fast, like as if I had written it myself?
Yeah, why do we like PyTorch? Because it lets us iterate quickly on ideas, right? Whereas if you need to then you have an idea, you need to translate it to a C program or a CUDA program, then it takes a whole lot of resources, knowledge, and so on. So PyTorch really democratized GPU programming in the end, right?
Right.
Among many other frameworks, but PyTorch did it for sure for AI. And if we could have both ways, that would be great. So if we could take a PyTorch program and make it really fast by having, not a human, but kind of a robot doing the work for us, right, and producing the program that we want to write here, right? We machine produce this kernel, which is a fused kernel, this is why it's called Fusion, automatically. That would be great. So what are the projects that would allow us to do that out there right now? There's one that is quite popular, more popular than Thunder. There are many of them, right? Yeah.
Yeah, so there's so many of them. One of the early ones maybe was Apache TVM, and it still has a very dear place in my heart. But probably the most well-known these days is Torch Compile from the PyTorch team itself. And that obviously takes PyTorch. And of course, before that, with Torch Script, one of the motivations for Torch Script initially, when you remember PyTorch 0.4 and 1.0, that was a representation of PyTorch programs. And then there were fusers, actually 3 of them, one first generation, 2 second generation. And they also, like very simple kernels, they could generate fused CUDA codes.
Yep.
And but nowadays we have Torch Compile, and obviously other frameworks like JAX do something like that under the hood too.
So JAX acquires the program in the same way and produces kernel. So like, can we identify the two big moments of a compiler? Because we already kind of understood here that we need to understand, right, what even we want to do, and then we need to translate it into something else, right?
Right. And obviously there's like many layers of this. So typically we have the program as written by the user first, for example, our PyTorch program, a PyTorch function. And then the compiler will take it and will have some sort of intermediate representation that is how the compiler sees the program, and it might have several layers of that actually. And then at some point, it has to generate the GPU code. And one way would be to go through CUDA code and then compile that. Another way could be to go through LLVM, which can generate PTX directly too. And so these are like the main things. And when you see a new deep learning compiler, you have these steps where they might be different. You have the acquisition, the front end bit, and then you have the intermediate representations, and that is also something that we will see down the road. That there's lots of differences. We actually looked at the traces, which are Thunder's intermediate representation last time. Um, and then there's the kernels that get out, and all these steps are very different because it's a young space, it's a very rich space that we're in with the deep learning compilers. And so there's lots of different approaches there.
Yeah, and I think it's a very interesting space for whoever is interested in digging to dig, because there's a lot of things that are going to happen in the sense that modern hardware needs very specific treatment in order to be fast. We are at levels where we're running things extremely fast, but to run them extremely fast and in very expensive setting, we need to optimize it. Optimize it. And fusion is not the only thing that happens to optimization. We mentioned distribution last time to run it on across machines, and we'll touch upon all that. But I would say we're about halfway through, and so with this like chart of the world, I would go into showing some code and see how we can represent in all these different frameworks an activation function, which is, by the way, something that is composed by many of these little functions together, and how we can see, how they get executed on the GPU. I'll pass it on to you.
Let's do that. So if I share my screen here, and I always get to do because I can't draw, I get to do the what's he doing programming bits. And so let's get right to it. And so to prepare, I have to admit I prepared a little thing ahead of time that will just be printing our things. We're going to use the PyTorch profiler, which is a very neat tool, just like PyTorch has many very neat tools. But so let's first get an activation function. What's your favorite activation function, Luca?
New Gelu or Gelu, whatever.
Yeah, that is actually a good choice. So we never rehearsed that or talked about it before.
Of course.
Obviously.
Yeah, what a coincidence.
So obviously this is like a very simple pointwise function, but I happen to know like how to write it. And it's basically, well, if we want a torch, it's a torch ton h, and then you need to have a normalization constant. And hopefully I get this right now, because otherwise I'm going to embarrass myself. And then there's a little Taylor expansion, and that is actually, I think, the thing that's the new Gello. Originally, you used the normal distribution CDF, and the new thing is to not do that. And obviously, I'm forgetting to import math here, right? And so this should be the new Gello, if I have any luck. And to have some input, I'm not going to be very creative here. I'm just going to use 5 times 5 random array. It's not going to do wonders because it's very small. It's not interesting from a timing point of view, but let's have it on the CUDA device here. And obviously, if you're doing that at home, I took a GPU here in my Lightning Studio. and you want to do that too, probably, if you want to play it.
Yeah, just go on lightning.ai, you sign up, you get in, you get free credits, you play with GPUs of different kinds, multiple of them, it's great. Just to clarify, what is NuGelu is, in the world of neural network, you have, for example, an MLP, so a linear, multi-layer per spectrum, right?
It's one of the activation functions. So if you have an MLP, which is linear layers and then a non-linearity, an activation function in between them, you need that in order, well, I'm a mathematician, you need that for the universal approximation theorem so that you can like have interesting functions. But so people have experimented a lot of deep learning obviously is experimentation. That's why we like the fast turnaround times PyTorch offers. And so people tried a whole bunch of things. In computer vision, Relo was the rage. And now for transformers, Gelo has been one of the things that people really like. But you see here that it consists of many like individual operations. And so if we run this in PyTorch naively, and we could even we could look at this in Python, right? So if I look at the function in Python, I see that, well, yeah, there's
whoa, what is this? What is this? Yeah, what sorcery did you play here?
Yeah, I used the Python disassembly module, and obviously we built a Python bytecode interpreter in Thunder, so I've played with this a whole lot. But basically, you see that there's things going on, like here's the binary multiply, then there's calling. Somewhere should be a method call. Call method here. This will be the tanh probably. And so it gets decomposed into many operations. And of course, PyTorch then, when tensors are involved, needs to do all these operations. We can see if I actually did that here well. So yeah, A not defined on my cheat sheet. That's with A. I have X here. You caught me. That's the thing about doing a live stream. But so we can now look what's going on when we actually run this by using the PyTorch profiler. And the PyTorch profiler, I just can't say whoever built it and contributed to it, it's an awesome tool. So before it was like a real hassle to get profiles and see even what kernels run. And now you just say here profile with torch profile as prof, so I get the object and I run this, and now as my cheating function from above that I just print the device times, which are the time that the profiler detected spent on GPU. And we see here, well, there's a whole lot going on, and so this will be POC, the POW function itself. But so this here is the actual kernel that's called. And so obviously PyTorch comes with, I don't know, 2000 kernels or so. It has templated vectorized element-wise kernels to have optimizations for all the element-wise things. And so here's a POW tensor scalar, and we have a 10H kernel here. And there's a multiplication probably somewhere. It should be a vectorized binary kernel. I can see it.
Yeah, something users usually don't realize is that when PyTorch executes, it has a lot of mechanisms to dispatch to the right kernel, and it has a lot of options to evaluate a lot of heuristics within PyTorch itself to look at what the input looks like, and some conditions that will make it select the best kernel to run in that situation. And this is something that is not just for every operation you have one kernel. No, you can have multiple choices and maybe also multiple kernels for one operation that just start.
Yeah, and one of the things that you also see here is that it doesn't really matter if I like assign this to variables in between or not, but each operation, if you run it naively, is like take the inputs and then compute the output and write the output, right? And so we can now run it through we can now run it through a compiler. And so, for example, we can use torch compile. So mygelo compiled. And this will be torch compile mygelo. And I can now do the same thing with torch profiler profile as prof.
There's a couple of R's in the. It's profiler.
That is the
Right.
Italian profile.
Exactly. Yep.
Yeah.
We're big on double consonants. Yeah.
So this could be this is the compiled function, and usually when you benchmark for seriously, you should have a warm up and all these things, but we don't need to care about it as much here. But yeah, actually we see now that there's an overhead. But if I do the same thing again and just run it, you will see the simplification. And so here you see that now, well, there's only one thing. So this is, unfortunately, it goes through the call stack and prints everything, just like we had the kernel and the function that calls the kernel separately here. But so basically, you just have one kernel that does the whole thing, right?
And what is Triton? What is Triton in this case?
Yeah, so Triton here is a compiler, actually another one developed by OpenAI that has a Python domain-specific language that compiles to device kernels. And so under the hood, Torch compile uses Triton. It doesn't generate the CUDA code directly, but instead it generates Triton code, and then that Triton code is compiled to the device code.
Yeah.
And that's just like Thunder will even go further and like not generate the code itself, but have backends that do that. For example, you can use Torch compile as a backend here, right?
Yeah, exactly. We'll get into the geography of things next week. But I think as we are talking about that, we'll develop the terminology and so on. So Torch compile is made by two big pieces. One is Dynamo and one is Inductor. Dynamo is the thing that acquires the program and it translates it into the IR and the intermediate representation. And then there's Inductor, which is based on Triton, and that it's one of the backends because Torch compile can target more than just Inductor, but it's basically the official one. That generates device code without CUDA. So Triton is another way to write the kernels, essentially.
I think Inductor also has like several backends that it can.
Itself. Yeah, exactly. Yeah.
But Dynamo is clearly the front end, and in the split into two parts, Inductor is the thing that kind of gets it from Dynamo and sees to having a kernel. Similarly, when we do this now in Thunder, this is and I'm going to do the warm-up right here with thunder.jit of the same PyTorch function because we want the PyTorch functions as what we compute. We can now also run the profiler. And you can actually profile any kernel calls. So we could also use JAX and then use the PyTorch profiler to see what kind of kernels JAX calls. So it's a very versatile thing. And it has a very neat interface. So here we profile our function and we print the device times again. And we see here, well, there's also like one kernel that is run, and we see this is an NVFuser kernel. And so this is from our friends at NVIDIA. They make the NVFuser, the software. And so if we look at the last traces, just like we did last time.
So NVFuser, just I'm interrupting just to put more color. NVFuser is what is the inductor to Torch compile. In fact, at some point there was, or maybe there still is, a backend for Torch compile that's based on NVFuser. So what NVFuser does is it takes a specification of a computation, it produces a CUDA kernel for that. And so you see the parallel between what inductor does, takes IR, produces Triton kernels that are then compiled to machine code, to device code, and NVFuser takes a specification of the computation, like do this and then do that and then do that, and then it applies very complex heuristics to then generate optimal CUDA kernels that represent the computation.
Yeah, so what Thunder does under the hood here is that it first, in its own, this is like a Thunder trace, which is the Thunder's intermediate representation. And from this, it generates a fusion specification that NVFuser will then take as input, and it will actually use CUDA as the IR and the output. And then it will pass it through the NVIDIA CUDA compiler, NVRTC, in order to generate a kernel. And so we see that here we have the IR, and it sticks all of our function into one big NVFusion, and then the NVFuser will actually handle it from there and produce eventually a kernel that can be just run from our Python code. And one thing I want to point out, like the numbers are very meaningless, but you see here that like one kernel we had here is about as fast as the combined kernel for either Torch compile or ThunderJIT. And that is because like the computation in all these little kernels is trivial. So what we're seeing here is loading from memory, saving it back. And if you only do that once, it's like running one thing, and there you have like a few arithmetic operations in between. That doesn't really affect the runtime. So we're being a whole lot faster here.
Which is the whole point of this, right? Not spend time where it's not useful, but just stick every computation here in a single kernel so you can execute that kernel. There's one caveat here, of course, if something changes of that computation. So if your program has a condition by which the program itself is a bit different, you need to go through recompilation again. And so we'll get more into these things later on, but I think this time we actually touched upon running things on CUDA, on GPU directly, and a way to see how many things are launched. And you can actually do it with your models, right? You take a random model, maybe not too large because it would be untenable, but you can take a smaller model or an attention block or one small transformer.
What I like to do is when I take a transformer, for example, from LitGPT, which is like what we work with most, then I just, there will be a module list that is the transformer hidden layers, and I just remove like 3 to 12 or 24 or so, and just keep the first 2. And that will usually be like a fast thing, and also the traces that you get will not be quite as humongous.
I would say that this we can do the next time live.
Yeah.
Well, sounds pretty interesting. All right. So thanks a lot. It's Friday. We deserve the weekend. So I hope everybody has a good time.
Yeah. And you have a good weekend too, because you deserve it too, obviously.
Yeah, you too. Thank you. Bye-bye, everyone. See you next time.